For our third experiment, number 23, cut short.
The purpose of this experiment is to show the law of conservation of energy using a pendulum. We use styrofoam for the base, an illustration board for support, yarn for the string of the pendulum, a jolene or marble for the pendulum ball, clothespins and chopsticks for the stands, a glue stick for attaching parts, and a candle to melt and secure some connections. The styrofoam was cut into three, then glued it to the illustration board who acted as the base of the whole setup. We glued 3 chopsticks upright on the styrofoam base to act as the ring stands. Then, we connected the clothespins to the chopsticks to make the base of the yarn that will swing the jolene. Next, we tied one end of the yarn to the jolene tightly and the other end to the top bar so that it could swing freely. This became our pendulum. We also made another horizontal string using yarn between the 2 chopsticks, about 2/3 of the way up to act as a stopper rod. This string will stop the pendulum halfway through its swing. To test the experiment, we pulled the jolene back and let it go. It swung down and up, showing how potential energy when raised changed to kinetic energy as it moved. When the yarn hit the horizontal string, the pendulum's length shortened, but it still swung upward, showing that energy was conserved, just transferred between forms. We adjusted the height of the horizontal string to see what would happen if it was higher or lower. Each time, we observed how high the jolene swung back. For step 4, our first prediction is that the ball will go higher than the horizontal string, and upon observation, the ball did swing a bit higher than the horizontal string. Therefore, our answer is letter A. For step 6, our prediction when the rod is higher than string is that the pendulum will be shortened earlier in its swing, so it will swing up higher than before. And based on our observation, the ball did rise higher than the horizontal string. When the string hits the rod sooner, the pendulum's radius becomes shorter, increasing its angular velocity and kinetic energy at that moment. The ball swings to a greater height due to the conservation of mechanical energy. For step 7, our prediction if the rod is lower than string is that the pendulum will be shortened later, so it will not go as high. And upon observing it, the ball does not go as high as the horizontal string. As the pendulum swings, potential energy at the highest point is converted to kinetic energy at the lowest point. When the pendulum's length changes by hitting the rod, the energy is redistributed, but the total mechanical energy remains constant, neglecting friction. The motion demonstrates the conservation of energy. Potential and kinetic energies transform into each other, but their total stays the same. Yes, the upper limit is the point where the rod touches the pendulum string when it is fully vertical. If the rod is any higher, the pendulum cannot swing freely or shorten properly. The motion will stop or the ball will hit the rod immediately. Yes, if the rod is too low, the pendulum will barely be affected. It may not touch the rod at all. At this point, the pendulum behaves like a normal, full-length pendulum and the cut short effects disappear. The rod must be positioned so that the string contacts it during the swing.